Good afternoon and welcome to Machine Design, New Equipment Digest, and EHS Today's webcast. Our topic today, Machine Guarding Technology, sponsored by Schmersal. I'm Jeff Kearns with Informa's Design Engineering and Sourcing Group. First, if any of you have any technical difficulties during today's session, simply hit the F5 refresh. Hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we will welcome your question during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the websites within the next week. You'll be notified by an email when the archive is available. Now let's meet today's speaker. Mike DeRozier is a TUV certified functional safety engineer for machinery. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now, let me turn things over to our presenter. Mike, the floor is yours.
Thank you, Jeff. I appreciate it. Hello, everybody. Thanks for joining us today, and I appreciate the time everybody's taken to learn a little bit about machine guarding technology. With a lot of subjects that we pick in doing these webinars, and you can see some linked to our website to see some of the past ones, such as lockout tagout versus machine guarding or fault masking. We picked those safety subjects to try to help people out on what they're trying to do with their machine guarding endeavors. And with this one, we thought we would try it a little bit different and talk about some of the technology nowadays that can really help people out with increasing their level of safety, as well as awareness and information to be more productive on a machine without sacrificing safety. We're not going to cover every single technology out there within a 45-minute hour time window here, but we'll try to highlight some of the ones that are currently available. But in doing so, what I'd like to do is kind of look at where we were, where we are, where we're going type of scenarios. And typically as humans, we learn and we get better at what we do as a result. And I love these pictures. I was taking a field trip one time at Smithsonian Institute, and I got a picture of these old antique fans that were in a case. And I thought this related really well to machine guarding. When you look at the design of fans, such as the one you see pictured way back when, the goal was to use this as a tabletop fan, cooling people off, do different functions as a result. But when you see a fan like this with an all-metal base, metal blades, direct drive motor, all the things that go along with this, in today's machine guarding world, we see nothing but a serious hazard as a result. And when you think of where we were versus where we are going to, you see the next migration in safety when it came to those fans. When the steel process or the steel industry came out with this new way of forming steel where you can basically have steel wire that was permanently shaped and bent into a shape, such as forming the guard on the fan, the initial thoughts were, wow, look how safe we made this fan. I've even seen old TV infomercial or movie infomercials that showed a little boy standing at the edge of the table with his face right up against the fan, and the exact comment was, see how safe we made it. Forgetting the fact that he can stick his fingers through that fan. But at that time, it was safer compared to the picture on the left. We did have a migration in safety. But if you look at today's world, we would never buy a new fan like this or a tabletop that was unguarded or partially guarded. It would be fully guarded. So the one that you see all the way in the right is what you get today. Have we improved? Absolutely. We've learned through the years. We developed more technologies as a result of learning. We get better. What do people want on a machine? When you think about the users, what do they need? What are they looking to do? What are they trying to do as a result? So where does technology really start versus where it's going? What I did is called this traditional versus modern. When we think about traditional machine safety technology, we think of nothing with microprocessors, no electronics. It's just straight types of switches, electromechanical switches, or hard relays that are wired up in a master control relay type of circuit, a latching circuit, things of that nature. So traditional electromechanical, hard stops, that kind of thing. When we look at modern safety technology, we're starting to see the migration, and we have over the last several years, of utilizing available technology. As more technology gets developed, the more we can implement and integrate into safety devices for machine safety. And that's all well and good. We can get microprocessors and electronics inside of switches and programmable safety controllers and safety PLCs. And even if you look at other devices that go along with safety, such as variable frequency drives, most manufacturers of drives that do VFDs or power inverters for motors have safety built into them now that are approved and rated for such. And a common term is STO, safe torque off. They have safe torque off capability. You can get drives or programmable controllers that can do live speed monitoring. You can connect encoders and resolvers to them that are safety rated in the controller, where you can monitor speed, a safe position, a safe direction, a safe indexing, which are things that we couldn't do from a safety perspective. We may have done them in order to try to get the safety, but the devices themselves were not safety rated. We have that technology now built into those different types of devices. So getting some of that safety motion, and now we have networks. Getting safety over a network is huge, where we can reduce the number of wiring and get more information across that network. So we're going to cover some of these different technologies as we go through the webinar today. But to me, one of the most important things is why. Why have technology if the traditional technology works and is considered safety rated? Several reasons you see listed there. When we say increased reliability, because you don't have the same mechanical parts that you do in traditional switches where you have more electronic, you don't have those physical contacts or physical breaks. Or reed switches, you have solid state type of devices where traditionally the electronic technology has a longer life cycle on them, a greater span of life to get that. In turn, in doing that, we can also have an increased safety level. Meaning with the electronic technology, because of the monitoring capability you can get built into those different types of devices, you can get an improved safety level. So when I say safety level, what I'm referring to is some people on the line would be familiar with control categories and performance levels. We have control categories B, 1, 2, 3, 4. Performance levels A, B, C, D, E, and SIL levels, SIL 1, 2, 3 when we talk machine safety. So the highest level of safety you can achieve with any of those is a Category 4 architecture, a performance level E to ISO 13849, or a SIL 3 to IEC 61508 or 62061. When you look at those different levels, sometimes when you're looking to achieve a higher level, it becomes harder to do with some of the traditional technology without adding more components to it and make a more costly system as a result. So with the electronic technology, we can increase some of those safety levels and maintain a cost-effective solution, increase our safety, thus increase in productivity. The next bullet point I think is huge among everybody out there. What are we looking for in today's world? We always wanted uptime. Nobody likes downtime on a machine. When a machine is down, it's not producing. Thus, the company's not making money. We want uptime on the machine. Yes, we have preventative maintenance functions. We have scheduled shutdowns. There's reason for the PMs to try to keep the machine running. But we all know it and face it. Reality is things happen. Things break. And when they break or something goes wrong, whether it's an internal break or external influence like shorting wires out on a machine, sometimes it gets very difficult to troubleshoot with traditional technology unless you add a lot of cost into the system. And then you can increase that response or that diagnostic capability by adding that cost and get the machine up quicker. But with electronic technology now, having that increased machine uptime, meaning if a failure were to occur and you can get that information and report back what device is having the issue, do you know what the issue is, where you can go fix it and get that machine up and running again without sacrificing safety and minimizing the impact on productivity, which leads into that more diagnostic capability. Getting more diagnostics, more information out of the system, out of the devices when it comes to the safety side. We're doing it with the non-safety. You see more intelligent sensors on a machine. You're seeing more intelligent valve banks, more technology in the PLCs or in the industrial computers, more software as a result, more processing information. We're getting more and more information because what you tend to see and what we're seeing is people are trying to get more predictive with what's happening, what's going on, more fine-tuning, more precise measurements, more precise production, but more information. And more information means getting more diagnostics. Safety is no different. Getting more diagnostic capabilities out of your safety devices becomes a lot more desirable because you can get more information, you can be more predictive, and you can get into the last 2 points with easier or reduced wiring because of how some of the connection capabilities can be with different manufacturers' safety devices out there now. So looking at a couple specific examples, when we talk switch technology, we first started seeing switches before safety technology was out there. People were using non-safety, what we refer to as negative operated, negative mode mounted limit switches on doors. You push the plunger, a door against the plunger, close the contact, make things work as a result. Allow the machine to run. Open the door, shuts down. There's definitely some issues with that design. So we come out with safety rated switches in different form factors. Now we have electronic switches. So I want to kind of cover a few of those different options. So when you look at the picture on the screen now, we have what used to be a non-safety rated limit switch. Non-safety. This is not safety rated. You close the door, it pushes against that plunger, that limit arm, whatever the design of that particular limit switch is, which closes the contact. When you open that door up, what happens is the spring pushes that contact open to break that circuit. It opens that circuit up to initiate a machine shutdown. The issues with this kind of design is it's not safety rated for a few reasons. One, if those contacts were to weld, those springs do not have enough force to break open a welded contact. If it mechanically sticks, the circuit stays closed. It can be easily defeated just by putting a piece of tape or a wire tie over that device, causing an unsafe situation, and somebody can get seriously hurt as a result. This is not a safety-rated device. So what did we do when I kind of look at where we were with the pictures of the fans, the first fan that was completely unguarded? Well, before we had the guards, we started putting guard doors. We used non-safety rated limit switches. Did we improve the safety situation? Yes, it improved for something that was completely unguarded. Did it necessarily make it safe? Well, then we started going with safety rated limit switches. So the fact that this isn't safe we came up with safety rated and came up with positive mode mounting, positive brake. What that means is when the door is actually closed, that's when the plunger or the arm is allowed to extend up for the spring to make the contact. Through the entire travel of that door opening, whether it be a sliding door, which is kind of what you see in the picture there, or a rotary door on basically a rotary cam, so a notch in that door so the entire swing of that door open puts pressure against that plunger. It forces that contact to open. You notice the arm may be a little bit thicker than the previous slide. It has more mechanical resilience. So even if that contact were to weld, it's going to break it apart, and breaking it apart ensures that you get a safe shutdown of your circuit. So when you look at what we had before, we went from an unguarded fan. We started putting non-safety rated limit switches. We put guarding, but it really wasn't a safe solution and made it better. Didn't necessarily make it a lot safer. Now we have safety rated devices. Now we look at more modern being the electronic technology. You can get different technologies in guard door interlock switches now. And I listed a couple examples with the RFID or pulse echo technology. You can get transponder technology. There's different technologies that different manufacturers of safety rated switches have. But at the end, what it is, you can see it is purely electronic. And the fact that it's purely electronic and you're using safety with known technology such as RFID, you have an actuator that comes in close contact to the switch. Well, now you can get more information. You can have additional door misalignment where it's not as tight as what the traditional switches used to be. These become much harder to defeat as a result because, in addition, one of the webinars we gave was on ISO 14119, which dealt with the updated version of guard door interlock switches and the different types and some of the things you do to make it tamper resistant. And part of that with tamper resistance to minimize your design changes is to go with electronic switches that you can actually code. You can teach to one another and reduce the additional measures that are needed to comply with tamper resistance according to ISO 14119. In doing so, because you get microprocessors inside these devices now, they do a lot of fault recognition within the switch body itself and the wiring of that switch body from the outputs going on to the next device, the safety controller, PLC, safety PLC, something like that. But in doing so, it means we get more diagnostic capabilities. So getting additional diagnostics such as LED diagnostics, where it's not just an open close. You can get LEDs that tells you you're getting close to the edge of the hysteresis now. You better come fix me because I'm going to stop working. You can get LEDs that have blink codes like you see in the little flash codes. A red LED flashes in different pulse increments to tell you what is the actual fault occurring on that switch. So now you can see we went from completely unguarded to using non-safety rated limit switches. We migrated into the safety rated limit switches and created a much safer environment. But now because we want more uptime and more diagnostics and more information and more tamper resistance and being more predictive now, we have the migration into the electronic technology as a result. When we look at the logic of a machine safety system, talking about the controllers, we started off with looking at single channel MCR circuits, a master control relay circuit. Then we added safety controllers, safety monitoring relays that were electromechanical relay based. We now have those safety monitoring relays with electronic technology in it from manufacturers all the way up to full-blown safety PLCs, programmable safety controllers, but just the basic standalone safety monitoring relay or safety controller with microprocessor-based technology in it now for all those same reasons we talked about: increased uptime, increased diagnostics, more longevity as a result. So let's talk about a few of those technologies. Real basic, simple pictorial circuit here. A latching circuit. You have that safety rated limit switch going to an NCR through a latching circuit. So that would be your reset button as an example. It latches itself on. You open up the door, the coil de-energized, shuts down. When you talk single channel circuits, single devices, the problem is any single fault can lead to the loss of the safety function. So we said, hey, how do we increase safety? We started looking at relay technology and creating redundancy and monitoring as a result. We improve. So within a safety controller, for example, and there's lots of different flavors and manufacturers out there with different bells and whistles on them, but at the core of it was electromechanical relays, mechanically linked relays inside. You can kind of see what's going on inside the basic safety monitoring relay. We created dual channel, so we got redundancy. That's what the CR1, CR2 inside that housing does. And then we have CR3, which is our monitoring. So if we get a single fault in one of those door switch contacts, we can detect it, still ensure the machine shuts down, and prevent the machine from resetting. And we can get more complex. We can add additional mechanically linked contactors to safely shut down motors and create redundancy and feed it back into that feedback loop. But I just wanted to show you a basic example of going from that single channel to the dual channel using mechanically linked relays as a technology inside these little black magic boxes. So where do we go now with the monitoring? I know it's hard to see when you look at this slide. You see the picture on the left doesn't look a whole lot different than the picture on the right as far as the schematic representation. Yeah, a couple little different terminals. It's not showing you what's inside. The picture on the left is basically what you saw on the previous slide with electromechanical, mechanically linked relays inside that housing. The picture on the right actually has microprocessor-based technology inside of it. So what does that really mean and look like? Well, what you have in there with the microprocessors is now you use, instead of looking at cross-short recognition through power supply means, such as a plus and a zero with internal electronic protection, you now have microprocessors that use test pulses. You see that on safety PLCs, programmable safety controllers. You now see it in microprocessor-based safety monitoring relays as well. What else does that give you? It gives you that longevity because everything is solid state inside versus the electromechanical relays. You still have electromechanical relay options on the outputs to interface with older machines, existing systems. But a lot of the technology nowadays, when you start implementing it, is looking more and more at solid state inputs. So for example, when you look at some of the robot manufacturers with their controllers, they're looking for a contact closure, but when you look closely, they're just looking for either two 24-volt signals or a 24-volt and a 0-volt signal as their redundant safeties into their robot controller for the e-stop and the protective stop of that controller. You look at drives, they're looking for a 24-volt signal. As long as they're sharing that common 24 volts, we may be able to get rid of some of the dry contact, thus increase some of the longevity of those components. But we talked about increased uptime. Well, we get increased uptime because we get more diagnostic capabilities. So when you look at this particular controller, you can see that there's LEDs on there. Well, with those LEDs, there's also a red error LED that will blink in different codes. You can look those codes up and see what is the exact fault so I can troubleshoot, fix the problem without bypassing it, and get the machine up and running and maintaining our safety and get the machine in production up and going as quickly as possible as a result. So we launched into the next generation of technology using those controllers as a result. What else does it do for us? I know I'm jumping back to switches here, but when you compare the information you can get from traditional electromechanical switches versus something that may be an RFID type of switch, you look at the pictures on the left. You got dry contacts there. Typically, the third contact may be used as your enunciation to an input to a PLC, so you know which door is open or closed. Or maybe you send it to a light on the panel to know which door is open or closed as an indication. But that's all it's going to give you is open or closed. It's not actually telling you if there's a fault on, say, the first normally closed contact. If there was a wiring fault there, you open up the door, that normally open contact will still open and close as a result. So it's not telling you that that particular switch is faulted. You get into different things like codomagnetic switches where you can get LEDs in those switches. And a lot of people think that that gives you full diagnostic capability. It gives you indication. And it's indication because that LED is typically in series with one of the contacts of the switch. And looking at that, and again, different manufacturers have different technologies in what they do, even with traditional electromechanical. But this is just one example where you open up the door or close it, the LED turns on and off depending on the state of that contact. But if there's an error in the other contact, you're really relying on the controller to let you know that that was the switch that was errored. In an electronic switch, typically you'll get 2 to 3 LEDs. So in the example I showed here, you got a green, amber, and red. Green may indicate power, where amber indicates your door status, where red will give you those individual fault codes. Why is this important to us? Well, when we look at how people traditionally wire switches up, it is very, very common for people to take door switches because it's one safety function for a machine and wire them in series to a safety monitoring relay. Anybody that has this type of system and anybody out there that is maintenance, I'm sure can attest that when you get a fault in one of these switches, it is time consuming to try to find that fault because you don't always get quick indication of which switch has the problem or where in the wiring the issue is occurring as a result to give you a starting direction. Hooking up to the controller to know maybe which channel is faulted out helps. But you see the couple of the bullet points up there, that potential for fault masking and what you can possibly achieve according to the control categories and performance levels. You may be able to achieve a Cat3 PLD, but anybody that's looking at CR24119, when you wire switches in series with commonly used doors, it drastically reduces your diagnostic capability and takes your performance level out of where you need. What if you need Category 4 PLE? There are definitely ways to do that with electromechanical switches, whether you put 2 switches per door, isolated contacts, or you use more coded magnet and separate inputs to individual safety PLCs or programmable safety controllers, or individual safety controllers for each switch to get more diagnostics and increase our safety level. This becomes much harder to troubleshoot, which may lead to increased downtime. So you look at those trade-offs of you add more cost to minimize the downtime, but in order to minimize downtime, you're adding more cost. So many times when people start looking at cost and adding a bunch of controllers or more switches or additional logic such as programmable safety controllers and safety PLCs and involving software now, they opt to go for something that's more economical, thus either sacrificing safety level or sacrificing diagnostic capability. Is there ways of doing this with electronic switches? Absolutely there is. You have to look at the manufacturer's specification sheets and what they're rated for, but many of the electronic switches that are currently available on the market, you can actually wire those in series and create that daisy chaining effect and actually achieve that highest level of control category 4 and PLE going to one safety monitoring relay or controller that's rated for that level as well. How is this able to be done versus what we know with the traditional switches? It's because each of these switches have their own set of microprocessors in them, like we mentioned a little while ago. As a result, it gets us the ability to avoid fault masking. And I mentioned fault masking was one of the webinars. You can go back and link to our webpage to see that webinar on fault masking, but I'll just overview it really quick. Fault masking is the ability of having a fault in one of your contacts of your switches. Let's say in the previous example, there was 3 switches in series. If there was a fault on the very first contact of channel 1 on door number 2, just opening up door 2 and closing it again, that safety controller would detect that fault and prevent you from restarting. But opening up door 1 or 3 actually clears the fault out, thus create fault masking, and you're able to restart the system without actually correcting the fault as a result. In an electronic series connection, because each device has its own microprocessors and doing their own fault diagnostic, if we get a failure, a short circuit, say on channel 1 of door number 2 in this particular example, opening and closing door number 1 does not clear the fault out of door number 2. The fault is still there because it's monitoring the outputs of its transistors and looking for that test pulse type of scenario with a lot of manufacturers. So you don't get the fault masking. And because each switch does its own monitoring and does its own cross-short recognition, you're able to get that highest level of category being category 4 or performance level E when it comes down to those type of circuits and connect to a very simple basic controller as a result. Okay, where are we going? Where do we see things heading, and what do we have in technology now with some manufacturers? Okay, we implemented the electronic switches where you have those standard diagnostics. So when you see the picture on the left, that little out terminal can be signals to a PLC for your door enunciation. It'll give you door status being open or closed, or maybe a misalignment out of the hysteresis, and give you more of a blinking type of code like the LED. But you can migrate it one step further and get something with serial diagnostics where the diagnostic wires are actually wired in series, and you can actually take all that fault information and communicate it up a field bus network, a standard non-safety field bus, because we're not talking the safety section. The safety is still tied into the safety controllers as it always has been, but the diagnostic information can now go up to a field bus network such as Profibus, Profinet, Ethernet, IP, the different field buses as a result. In doing that, what you can now get is more information as a result. So what you see in this picture here is a few door switches connected in series. The yellow lines are still connected to your safety monitoring relay, safety PLC controller, but the serial diagnostic line is connected into that interface to go to whatever field bus network you have, such as the Ethernet IP or Profinet as examples. Okay, great. What does that do for you? Well, what it means is for each individual switch now, because they become an address on that serial device network, you can actually get data byte information. So you can get bytes of data that tells you individual status of each individual switch. You see a chart here giving some examples. Knowing you have the inputs to the switch, knowing that the outputs are on, knowing that the actuator is detected so your door is closed, knowing when you got a fault in the system. Those bits go high on bits 6 and 7. You now have diagnostic information. Hey, you got a short circuit on the first output, or you got a cross short if that bit goes high. You can get more information. That's awesome, because what can you do with that? We can now become more predictive. We can be more responsive in solving issues on a machine when it comes to the safety side of things now. So when you look at the example on the slide I have right there, we have 12 doors connected in series. And as I mentioned, any engineer or maintenance that has seen or worked on this kind of system, troubleshooting on a traditional electromechanical switch becomes very difficult. Well, in this system, what we see is our two lines going down to our safety controller to safely shut our machine down, do its monitoring. Each switch has its own diagnostics, and you can see the LEDs on the switches, but what you now see is a serial diagnostic line that if you look closely at door 5, there's a red LED that's on right now. But now that you have your PLC and your HMI connected to the machine and that diagnostic information is going in there, you can program all those data bytes to report a message. So here on the HMI, we have a fault in the safety system, and it's telling you door number 5 has a short circuit detected on its second output. Go fix it. Get the machine up and running again. Find out where that failure is within that door switch. You can now go to that switch and trace down from the switch down to the next one to know or find where that fault is and get your machine up and running as quickly as possible and solve the issue without sacrificing safety as a result. Now, the next thing I said, or toward the end of that list of what does technology give us? Well, the more technology tends to create more wires as a result. So you can have all your wires individually wired, which is pretty traditional, going to junction boxes or home run back to the main panel. We can now have distributed safety I/O modules and blocks, or we can do safety over field bus. So I'm going to cover a couple of those examples for you. So when we look at what we have, we'll take that same situation, electronic switches, we got 12-volt Voltman series, but when you look at the potential of multiple wires per switch and bringing those back, what are we really looking at? We got a bank of terminal blocks inside a junction box or the main control enclosure. We're bringing all those wires to as a result. And that may be the ideal situation for that particular machine, and there's nothing wrong with doing it this way. But sometimes with the technology and what you can do and avoid some of those fault masking, more technology has been developed to make that easier. And one of those is distributed I/O blocks specifically designed for safety. The nice thing about something like this is here you have this system with 3 distribution blocks. We still have our 12 doors, but what do we have going back to our main panel in essence is 2 cables. 2 cables go back to that main panel, and we have more of a plug-and-play system. What does it help with? You get a switch failure or a block failure. It's much quicker and easier to replace with something that's more plug-and-play. The fact that it's plug-and-play, you have easier installation as a result. So when I mentioned at the end of the first couple slides looking at easier wiring and reduced wiring, it's because of being able to take some of the safety technology and do more of a plug-and-play system without losing diagnostic capability as a result. So here's that example with the same serial diagnostic network. You can go through that distributed I/O plug-and-play, go to a programmable safety controller that has that information exchange built in, come across Ethernet IP or Profibus into your PLC to flash that message up on the screen. We have the same fault as we showed in the previous few slides with door 5 being faulted. There's a short circuit. Time to go find where that short is and fix the problem as a result. I also mentioned safety technology being built into speed monitoring. Now you can get drives such as servo drives that have different speed monitoring functions built into it, not just STO being safe torque off. You can get things like safe 0 speed or SLS being safe limited speed. You can get safe direction or safe jogging, safe indexing, that kind of stuff. That's great on new installations, and sometimes it's cost effective to replace the older technology with the drives that have that capability into it. But what about the scenarios such as a VFD where you're controlling speed, but you don't need the functions of a servo, but you still need speed monitoring functions? Well, you can get programmable safety controllers or standalone controllers that do speed monitoring that looks at encoder feedback as a result. So when you look at that encoder feedback, you can set up parameters to say, what is the safe speed? Well, why do we need something like that? If you think about some of the machines that you may have built or seen out on the floor, not every machine is just load raw materials, walk out and hit start and everything just goes and the finished goods come out the end. That would be great if that was reality. But living in the real world, we know some machines, particularly when you look at things like textile machines, scroll forming machines, you can't always start threading up a machine in a standstill condition. So doing a slow speed or a thread up speed as a setup procedure that's monitored, that you're always running at a safe speed to minimize injury, reduce risk, or even create an indexing so it can only jog a certain amount to avoid somebody getting drawn into a machine because of where those nip rollers are. Because if it over travels at that point in time, you can create an e-stop on the machine. That's where some of these speed functions come in. Well, what did we do before this capability was built into different types of manufacturers' drives or different manufacturers' programmable controllers or standalone speed monitoring modules? They didn't. That was the problem. They would go into an existing drive and just maybe set an input to say run at this speed or put a jog button there, but there was nothing preventing it from a safety perspective that if it were to fault or run away to safely shut the machine before somebody got hurt. We now have that capability in technology to monitor things like that and create a safer environment and lower our overall risk analysis at that point and our risk assessment and our risk factors and hazards associated with the machine. The next thing that we see in the migration is safety over field bus. Well, we have field buses. I said Ethernet IP and EtherCAT, Profinet. There's DeviceNet. Well, they now have the networks where you can communicate safety across it. The example I'm showing here happens to be an AuxiSafe type of network. It's a two-wire safety network, but it's a network that's used for safety and not safety components. But you can do safety over a network. This happens to be what they call safety at work. So it's AuxiSafe type of technology where you can get different manufacturers' switches and connections and drives and different devices that are safety rated. You see there an e-stop going to some switches, but they're not necessarily wired in series. They go to a safety monitoring relay, and in there, whether you have a programmable safety controller, you can set up zones and do different things, or you're shutting two redundant mechanically linked contactors down to shut your motor down. This drastically reduces wiring over a machine and still give you some diagnostic capability across those two wires because it's on a safety network. It's a safety approved network. Where is technology going? A lot of you may have heard this, Industry 4.0. There's white papers on it. We have white papers on it. I think there's some links there. If not, we can send them to you. But it's putting safety on the cloud, not necessarily having all safety communication on the cloud, but we said being predictive, being able to extrapolate data, being able to log data, such as how many times was a door open, how long was that door open, and become more predictive on life cycles of devices or how they're used and how that can help your risk assessment process. Being able to take all that data, put it up into a cloud, and be able to extract that from the cloud across, say, a facility, a plant floor. Being able to pull all your safety information right out of a cloud up to your network and communicate, whether it be wireless, on a server, but basically that Industry 4.0 is being able to become more predictive and get more and more information. This is where the future is going when it comes to safety technology. We have the electronics, we have diagnostic capabilities. We're now developing the cloud. You got manufacturers developing devices for this Industry 4.0. And again, not that there's a lot out there for it right now, but there's either some components out there or more that's in development where you can communicate OPC and things of that nature up to that cloud, and again, being more predictive as a result. So at this point, I think we hit our time pretty good. It's time to open up the questions.
Okay, thank you. And our first question is, can e-stop be wired in series?
Depending on your level, but traditionally when you look at e-stops can be wired in series, and you can certainly achieve with a series connection a Category 3 performance level D traditionally, and there's nothing wrong with that. It's actually very common. E-stops, when you think about in practical purpose, do not see the same issues as you do with door switches. And what I mean by that, even though mechanically they're wired the same, they two normally closed contacts, or one normally open, one normally closed contact, wired into that series parallel connection. You bring them back to a safety controller, but hitting one e-stop and having a fault in one channel, it's not like typically people are hitting another e-stop to clear that fault masking. However, it is a potential. But the biggest issue is more on the guard door switches, where it's very common to open up multiple doors and see a fault go undetected. So wiring e-stops in series traditionally, from what I've seen out there and from most people's interpretation, it's not an issue wiring them in series as long as you wire them properly, you're using the proper safety controllers for the proper safety control categories, performance, or SIL levels that you need for that particular emergency stop system. It gets still a little bit harder to troubleshoot, but you can get individual diagnostics out of it with a third contact, and it's the same issue with troubleshooting as door switches, but you don't tend to see it as often because e-stops are not nearly demanded quite as often as what a guard door interlock would be. You know, e-stops are one of those things, hopefully you never need it, but you test it more often than you need it is the hope.
And since OSHA codes are outdated, what is OSHA view on this new machine safety technology?
OSHA does not deter anybody from using any type of technology. As a matter of fact, they don't differentiate in anything that I've seen or read between traditional electromechanical versus electronic when it comes to when you look at 1910.212, which is the machine guarding standard. And when you look at the publications, what are they really looking at on a general basis? You look at things like the general duty clause. Need to protect your people from serious harm or fatality from known and recognized hazards, as an example, in the general duty clause. When you look at 1910.212, and you read some of the verbiage in there, it basically tells you that we're not saying things have to be boxed in. There are different guarding technologies out there, such as safety sensors and two-hand control and hard guarding and things like that. They realize that there's different technologies out there, and as long as it's maintaining a safe condition for people to use, if anything, what you're doing is you're seeing an increased safety level over what may have been done traditionally. So if you have identical systems wired up the same way, you may get to the same safety level, but you also may increase your safety level and make it a safer system that's more productive with more information. And if anything, I think I've seen, talking with some OSHA people and inspectors and trainers, having the technology, they're actually looking for it. And I can come up with one scenario. I talked with an OSHA trainer out at the International Robot Conference. We were both speaking out there. And being involved with stuff like this and understanding the robot standard is what he teaches his inspectors to look for, because they know there's things out there to help maintain a safety level, and the OSHA inspectors need to ask for it. So I haven't found any OSHA inspector or any instance of an OSHA inspector diminishing any type of modern safety technology, because their goal is, how do we make people safe? And some of the technology that has come out, traditionally on older machines, you may not have had any safety on there. So the fact that they're seeing safety on those machines now and increased safety levels to protect people, I think OSHA inspectors will love. I hope I'm not speaking out of turn on that for the OSHA inspectors, but the fact that they're seeing some of the safety get put on some of the older machines because the technology's there to help increase the safety level and provide protection with still being able to work with the machine is better than an unguarded machine as a result. So I know it was a long way of saying, I think OSHA inspectors, from what I know and from what I've seen and from what I've heard, haven't had any issues with modern safety technology.
Oh, thank you. And while we're answering your questions, if you would like to submit one, please just type your question into the question window on the side of your screen and hit the submit button. And while we're answering some, please complete the feedback form, which is located at the bottom of your screen. The next question is, what is the best safety technology to use?
I don't know if there's a best one to use. The best technology out there is really, depends on the application. You saw different technologies in today's presentation, but ultimately I don't think there's necessarily one better than another. If you look at the application and what you need to do on the machine and what information you want to gather. So, for example, one machine, given the number of doors, it may make sense to home run the cables versus the cost of a distributed system and a programmable safety controller. You don't need the speed monitoring. You just need a standard safety controller, but you want the diagnostic capability. The next machine, it's got a lot more doors, and it makes a lot more sense to make it more plug and play. So you want more of that information to be able to quickly troubleshoot that machine a lot easier, and it makes more sense. So I don't think there's one technology that stands out above another. And I mentioned that I didn't cover every single technology that's commercially available in the market right now, but there's definitely a lot of them out there. It's just what's going to be best suited for your application for the things that you need to do.
And how can we apply new safety technology to machines where it's unsafe or impractical to use electronics?
Sorry, I'm thinking about that question. Read that one more time for me, Jeff.
Sorry. How can we apply new safety technology to machines where it's unsafe or impractical to use electronics?
Well, when you look at the different safety level, and forgive me if I'm not answering the question of how it was asked, it's just how I'm interpreting it right now. When you look at the different technologies, so for example, when I mentioned serial diagnostics, it may not be practical to put serial diagnostics in the system. It doesn't mean that you have to stay with traditional safety devices. You can still use electronic safety switches and get those LED diagnostics. You just may not need or have a practical purpose because you don't have any field bus networks in your facility or on that machine, because then it's just information that's not going anywhere as a result. You would use a standard electronic switch and still get that. You could have cases where electronic switches like RFID, if a machine generates a lot of RF and it's going to interfere with the RFID tags as a result, well, then you wouldn't use RFID electronic switches. It may be better to use something that's not susceptible to RFID, such as a pulse echo or transponder technology that is more immune to RF type of interference. There might be some machines, such as getting into some of the areas where it's hard to get wiring out to there for that extra signaling or their longer runs. Maybe that's where a safety network would come in handy, like an Aussie type of network. There's a lot of space between devices where an Aussie system may be a perfect system for something like that. But let's say a particular electronic switch or any electronic switch does not fit an application really well, that maybe the application, the traditional electronic, like a coded magnet or a key interlock switch, may be the best thing for that particular application. You run that back into your panel, into a safety controller. That doesn't mean you cannot get the diagnostic capabilities out of it, because you can go from that standard relay-oriented safety controller to an electronic safety controller and get microprocessor-based diagnostic information out of it with those LEDs and those pulse codes to help troubleshoot. When it comes to wiring those switches in series, that might be your trade-off to say, well, maybe it makes more sense to put some more money in the panel and bring each switch back individually and wire them up to their own safety controller, so we don't have the issue with fault masking, and we can get more diagnostic capability, at least point us to one particular door as an example. So I hope I answered that on how that was asked.
Well, we are running a little short on time. I'm going to just try to stitch these two together for you. One, is there any limitation of number of devices on a safety network? And with the idea of wireless devices becoming popular, will wireless networks ever be feasible to be used for a safety system?
Ooh, I'll try to answer this in the 4 minutes we have left. That's a tough one. Well, the first one is fairly easy. The short answer is it depends on the safety network. So, for example, on an Aussie network, you can have 31, and depending on the AB system, you can have 62 slaves, but traditionally you have a 31 max of slaves on a safety Aussie network when you look at the safety at work. When you look at something like a series connected non-network type of basis with like a lot of RFID switches, your limitation isn't necessarily the number of switches, but the length of your wiring because of voltage drop. When you look at the 24 volts, you tend to have a maximum cable length because of the impedance of the wires. So you can have a lot of switches in a small area, but less switches over a longer area because of voltage drop, and that's usually more of your limitation. When you look at some of the networks where if you have devices that connect right to Profi NetSafe or ProfiSafe or Device NetSafe or safety over Ethernet with CIP safety, those kinds of devices, the limitation is more of the safety field bus itself. So there's not one straight answer that says this safety network over this one, they're all maxed at these number of slaves. It depends on the individual networks that give you your limitations of physical addresses because the switches get addressed. When you look at something like the serial diagnostics I showed you, there's a cap of 31. That just happens to be the limitation of number of addresses associated with that particular serial diagnostic network. The next part, this one's a little bit harder. Where do we see wireless? Wireless, I've seen it in cases. One of the biggest problems that I have seen with wireless and safety is the bandwidth. When you look at the bandwidth, when you go across the globe, bandwidths are not the same. And acquiring a bandwidth that's dedicated to the safety, you actually have to acquire bandwidths in different regions and different countries because you can't use the same bandwidth, where a bandwidth in Europe is going to be a completely different bandwidth in the U.S. just because those bandwidths are occupied by other wireless technologies. The other aspect is looking at the interference and the fault. So there has been some wireless technology developed with safety, particularly when you see some of the e-stops, for example, like wireless cranes, for example, on the pendants. When I say wireless cranes, the wireless pendant for an overhead crane, you see some of that. Is it coming? With more stuff being developed over the cloud, I think it becomes more of being able to establish, can you get the bandwidth from a manufacturer acquiring a bandwidth? Is it dedicated for safety? Can it become more universal, or is it more regionalized at that point in time? And how much do you need wireless safety and dealing with the batteries or the charging of the safety device at that point in time? So we say, for example, you get wireless safety on a guard door interlock switch. It's still going to have a finite life as far as the battery is concerned, and looking at the maintenance of that and how do you ensure the safety condition of communications. I think that technology is there. So I think it's more of the bandwidth and the need, the demand. I think the more demand for it goes up, more manufacturers of safety components may look at that more to see if the cost justification is there, because doing wireless safety right now is going to be a lot more expensive than the traditional safety. What kind of interference is that wireless communication causing as well with other radio signals, and being able to filter those out to avoid an unsafe situation is the other concern. So, yeah, there has been some wireless safety, but I think it's still quite a bit of ways away from being reality based off of demand, but that's just an opinion.
Okay, thank you. And that is all the time that we have today. If there were any questions not answered during the live event, we will be in touch afterwards. That concludes the presentation. On behalf of Machine Design, New Equipment Digest, and EHS Today, I'd like to thank Schmersal for sponsoring the event today, and for all of you for attending. Have a great rest of your day.